Have you ever stared into the night sky and wondered, how did it all begin? This profound question has intrigued humanity for centuries. It's a question that leads us to explore the vast cosmos, unveiling the secrets of stars, galaxies, and the very fabric of space-time itself. It's a question that drives the field of cosmology, the science of the universe's birth, evolution, and eventual fate. Today we dive into the fascinating world of cosmology, exploring the origins of our universe. The most accepted scientific explanation for the origin of our universe is the Big Bang Theory. This theory, in essence, suggests that our universe started as an infinitely dense, hot, and small singularity around 13.8 billion years ago. From this singularity, it began to expand, and it continues to do so even today. Imagine a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point. Similarly, the Big Bang Theory postulates that every part of our universe is moving away from every other part. It's a concept that's quite mind-boggling, isn't it? Now, you might be tempted to ask, what was there before the Big Bang? Well, according to the theory, the concept of before doesn't apply. Time and space as we know them began with the Big Bang. So, it's like asking what's north of the North Pole. Intriguing, isn't it? But the Big Bang Theory isn't just about the birth of the universe. It's also about the creation of time, space, matter, and energy. As the universe expanded and cooled, matter and energy formed, followed by atoms, stars, galaxies, and eventually, life as we know it. Now, it's important to note that the Big Bang Theory is not a detailed description of how the universe evolved. Instead, it's a broad framework within which we understand the universe's past, present, and future. It's a scientific model that has been corroborated by a wealth of observational evidence, which we'll delve into in the next scene. The Big Bang Theory, though simple in its core idea, has profound implications for our understanding of the universe. It invites us to ponder on the grandeur of the cosmos, the laws that govern it, and our place within it. As we continue to explore the universe and its origins, we find ourselves drawn into a journey of discovery that is as vast as the universe itself. But how do we know the Big Bang actually happened? What evidence do we have? Well, we have a wealth of observations and scientific findings that lend credence to the Big Bang Theory. One of the most pivotal pieces of evidence is the discovery of cosmic microwave background radiation. It's a faint glow of light that fills the universe, almost like an afterglow of the Big Bang, and it's the oldest light we can see. In the early 1960s, two radio astronomers, Arno Penzias and Robert Wilson, stumbled upon this radiation. They initially thought it was noise from their antenna, but it turned out to be evidence of the Big Bang. This radiation is incredibly uniform, which fits with the idea of an evenly spread singularity at the start of everything. We also have the redshift of galaxies as evidence. As the universe expands, light from distant galaxies gets stretched, or redshifted. The further away the galaxy, the more its light is redshifted. This phenomenon, discovered by Edwin Hubble, points to an expanding universe, which aligns with the Big Bang Theory. Moreover, the distribution of light elements in the universe gives us clues about its origins. The Big Bang Theory predicts that hydrogen, helium, and traces of lithium should have formed in the early universe. And guess what? When we look out into the cosmos, that's exactly what we see. These elements are the building blocks of stars, galaxies, and ultimately, life as we know it. Finally, the large-scale structure of the universe also supports the Big Bang Theory. The distribution of galaxies on a vast scale, in clusters and superclusters, can be explained by tiny fluctuations in the density of the early universe. These fluctuations, visible in the cosmic microwave background radiation, were the seeds that grew into the cosmic structures we see today. These observations and evidences are the pillars upon which the Big Bang Theory stands. The Big Bang not only created the universe, but also the building blocks of everything we know. In the immediate aftermath of the Big Bang, the universe was an incredibly hot and dense soup of particles. As it expanded and cooled, protons and neutrons began to form, and these particles combine to create the simplest and lightest elements, hydrogen and helium. But what about the rest of the periodic table? Where did that come from? Well, the answer lies in the stars. Inside stars, nuclear fusion processes take place, squeezing together the nuclei of lighter elements to create heavier ones. This stellar alchemy is responsible for creating elements from helium all the way up to iron. Elements heavier than iron, though, are created in the explosive death throes of massive stars, in supernovae. These cataclysmic events spew out the heavier elements into the cosmos, enriching the universe with the raw materials for future stars, planets, and even life itself. From the stars to us, everything is a product of these elemental formations. Scene script. Yet, the universe is not just made of what we can see, there's more to it. Imagine walking into a room, and you can only see about 5% of what's inside. That's kind of how it is with our universe. The stars, galaxies, and everything we can observe are just a tiny fraction of what's out there. The rest is dark matter and dark energy, two enigmatic entities that make up around 95% of the universe. Dark matter, despite its ominous name, is simply matter that we cannot see. It doesn't interact with light, which means it doesn't emit, absorb, or reflect it. Yet, we know it's there because of the gravitational effects it has on visible matter. That's like knowing there's a wall in a dark room because you bumped into it. On the other hand, dark energy is an even more mysterious beast. It's a hypothetical form of energy that permeates all of space and is believed to be the driver behind the accelerating expansion of the universe. Imagine blowing up a balloon and then finding it's expanding on its own. That's the kind of surprise dark energy presented to scientists. These two dark entities, though elusive, are crucial parts of our universe's makeup. They shape galaxies, influence the universe's expansion, and possibly hold the key to understanding its ultimate fate. Dark matter and dark energy, though unseen and mysterious, play an integral role in the fabric of the universe. As we ponder on the origins of the universe, it's natural to also wonder about its fate. Like the final pages of an enthralling novel, the destiny of our universe is a subject of intense speculation and curiosity. Let's journey into the realm of cosmic future. One possibility is the Big Freeze. This scenario suggests that as the universe continues to expand, it will eventually cool and grow dark as stars burn out and galaxies drift apart. It's a bit like a grand cosmic retirement, where everything gradually slows down and fades away. Another theory is the Big Crunch. In this case, gravity could eventually halt the expansion of the universe, causing it to collapse back in on itself in a fiery, cataclysmic event. It's the polar opposite of the Big Freeze, more like a reversal of the Big Bang. Then there's the concept of eternal expansion. Here, the universe continues to expand indefinitely. Galaxies would continue to drift apart, becoming isolated islands in an ever-widening cosmic sea. These are but a few of the many theories. As our understanding evolves, new ideas may arise and old ones might be discarded. But one thing's for sure, the universe's story is far from over. While we may not know the exact fate of our universe, we continue to explore and understand its mysteries. From the Big Bang to the vast expanse we see today, the universe's journey is awe-inspiring. We've journeyed through the cosmos today, exploring the most prevalent theories about its origins. We've delved into the Big Bang theory, the formation of elements, the enigmatic dark matter and dark energy, and even speculated about the universe's fate. Through the cosmic microwave background radiation, we've glimpsed the universe's baby pictures, and in the stars and galaxies, we've seen its adolescence and maturity. We've witnessed the birth of elements, from the simplest hydrogen and helium to the more complex compounds that make up the world around us. We've grappled with the unseen and unknown, dark matter and dark energy. Though they remain elusive, their influence is undeniable, shaping the universe as we know it. And we've dared to look into the future, considering scenarios from the Big Freeze to the Big Crunch and the possibility of eternal expansion. But the quest doesn't end here. Every new discovery about our universe's origins opens up more questions, pushing us to continue exploring. This is the beauty of science, of cosmology, the endless pursuit of understanding, the insatiable curiosity about our place in the cosmos. As we discover more about our universe's origins, We also discover more about ourselves. After all, we are all made of stardust.